So far in this course, the only kind of functions that you've seen are linear functions, value function, and all the linear functions form a sort of family or a collection of functions that have some kind of property. In that case, the property that they have in common is that they're lines. Today we're going to talk about another family of functions called the absolute value functions. These will be a little bit different shaped than a line. All right, and also using this absolute value function, we're going to learn about how to transform functions. That is, how is one function related to another? Can you shift one and make it into another? So the first thing we will do is we're going to sketch the graph of y equals the absolute value of x by plugging in the points that are given in this table. And remember that when you plot a point, you go over the x and up the y. And then we want to know what shape does this graph have, what is the domain, and what is the range. Now also remember that an absolute value is a distance from 0. So when I say take x equals 4 and plug it in, the absolute value of 4, well, 4 is 4 units away from 0. So for that point, the coordinates are 4, 4. We go over 4 and up 4. So there's our point. When I input 3, I get that y is the absolute value of 3, which is just 3. So over 3, up 3. If I input 2, absolute value of 2 is just 2. Over 2, up 2. Input 1, absolute value of 1 is 1. So over 1, up 1. If I input 0, the absolute value of 0 is 0, because 0 is no units away from itself. With negative, so absolute value negative 1, how far away from 0 is negative? 1 will just 1 unit away. Absolute value of negative 2 will be 2, so that's back 1, back 2, up 2. Absolute value of negative 3 will be 3, and the absolute value of negative 4 will be 4. And of course, we could plug in more points and get more of a picture, but we can see that this extends out in that direction forever and ever. On the left, we are extending out in that direction forever and ever. Basically, we have two lines. The one on the right-hand side has a slope that is the right-hand side over here. That has a slope of positive 1. On the left-hand side, that line has a slope of negative 1. Okay, now let's just do review domain, range, shape, and domain and range. So the shape of this graph, it's not a straight line anymore, it's an absolute value, and it makes a V shape. How steep that V is depends on a couple things, and we'll talk about those later in this lesson. Now the domain is all of your inputs, so you look at your graph from left to right and see, is there a leftmost point on the graph, is there a rightmost point? And the answer is that there isn't a leftmost point because this goes over and up forever. And there isn't a rightmost point because this goes over and up forever. So that domain is all real numbers. Which you can express with this symbol, with an R with two lines, or you can give as negative infinity to infinity. Now for the range, remember that you look from lowest y value to highest y value. And there is a lowest y value. The lowest y value here is 0. There is no highest y value, so that means you have infinity on the other end. So remember, we include 0 with a square bracket up to infinity. So that's the graph of the basic absolute value function. And now we're going to look at how some other functions are related to it. So here we have the graph of absolute value of x plus 2. And because those absolute value bars are around the x, they mean do the absolute valuing first and then add the 2 on. So for example, if we input 3, we get the absolute value of 3 plus 2, which is 3's absolute value is 3, and 3 plus 2 will give us 5. So over 3, up 5. The absolute value of 2 plus 2 will just give us 4. So over 2, up 4. If I input 1, absolute value of 1 plus 2 will be 3. So over 1, up 3. If I input 0, absolute value of 0 plus 2 is 2. Negative 1, absolute value of negative 1 plus 2. Well, when you absolute value negative 1, you get positive 1. And 1 plus 2 is 3. Oops, not there. That doesn't look right. Over there. There we go. Absolute value negative 2 plus 2. So that'll be 2 plus 2, which is 4. And then lastly, absolute value of negative 3 plus 2 will give us 5 again. And you can see that you have that V shape coming out again, the same as in example 0. But this picture, think how is it related to that example, that picture from example 0? It's just the graph from example 0, which I'll draw in like yellow because you'll see that if you look at the video. So there's the basic graph, which I'm going to call the parent graph. And that graph, every point on it has been shifted up 2 units. So the graph of y equals absolute value x plus 2 is the graph of y equals absolute value x from example 0 shifted up 2 units. I mean, the basic idea there is you take the original y's, which were absolute value x, and you add 2 to all of them, which does make the graph go up. And if adding 2 makes the graph go up, it's likely that doing absolute value of x minus 3 is going to make the graph go down. But let's plot some points to be sure. If I input 3, absolute value 3 minus 3 will give us 0. Absolute value 2 minus 3, well, that will be 2 minus 3, which is negative 1. Absolute value 1 minus 3 will be 1 minus 3 or negative 2. Absolute value of 0 minus 3 will be negative 3. Absolute value of negative 1 minus 3 will be negative 2. Absolute value of negative 2 minus 3 will be negative 1. And the absolute value of negative 3 minus 3 will be 0 again. So over 3 up nothing, over 2 down 1, over 1 down 2, over 0 down 3, back 1 down 2, back 2 down 1, back 3 down none. And you can see that V shape again. And I'll sketch in that parent function again. So approximately, it's hard to draw straight lines. But you can see that this parent function shifted down 3 units is what produces the graph. And so from here on out, I actually don't want you to plot points. I want you to say, know what the parent points are, and then very carefully shift them according to what the graph says, what the equation says to do. Like if I had absolute value of x minus 5, you'd take your parent function and shift it down 5. So this is the graph of y equals absolute value of x shifted down 3. And so here's a general summary of that. So this is true so long as your k is a positive number. The thing we're going to talk about here. So you have to kind of assume that, and I should have written that down, but you know, stuff happens. So assuming you have a positive number, if you take the absolute value of x and you add that positive number, you translate or shift the absolute value x parent graph up k units, just like we did in example 1a. And if we take absolute value of x minus k, then we shift the graph of absolute value of x down k units. And if you think about it, you can see why I had to make sure that k was positive, because if k was negative, absolute value of x plus a negative actually would be a downshift. But you get the idea. So adding inside the absolute value bars is a little bit less intuitive, and so it's pretty obvious from plotting points what the shift is, but it is not what you expect. Like, this is not going to be a shift of the absolute value of x graphed forwards 2. It's actually going to be backwards 2. And so let's plot some points and just verify that. So here we have to do the stuff inside the absolute value bars before absolute valuing. That's kind of like PEMDAS, where we do stuff in parentheses first. So we do absolute value of 2 plus 2. So first we add 2 plus 2 and get 4. And that absolute values to 4. So over 2, up 1, 2, 3, 4. Absolute value of 1 plus 2 will be the absolute value of 3, which is 3. So over 1, up 3. And then inputting 0, I got 0 plus 2, which gives us just 2. which absolute value is to 2. Okay, -1, absolute value -1 plus 2. So first you've got to add the -1 and the 2, which makes 1, which absolute value is to 1. Okay, and -2, absolute value -2 plus 2 is absolute value of 0, which gives us 0. -3, absolute value -3 plus 2. Well, that will be absolute value of -1, which is 1. So back 3, up 1. And lastly, -4. -4 plus 2 is -2, which absolute value is to 2. And you can see if I were to plug in, say, -5, I would get this point here. And if I were to plug in -6, I'd get this point here. So once you plug in points, eventually after enough of them, you're going to see that V shape again. And so compare that to the parent graph from example 0, which I'll sketch back in. That parent graph from example 0 looks like this. Well, that's that graph shifted left 2 units. So adding a number inside the absolute value bars shifts the graph left. Another way to think about it is that it keeps the original function stationary and shifts the x-axis forward 2 units. So it moves this thing over 2, which puts this point that was at 0 now at -2. I mean, that may or may not be the best intuitive explanation. It's up to you if you like it or not. But what you have to remember is that if you add a number inside of a function, it's a shift to the left. And correspondingly, if you take away a number inside of a function, it's going to be a shift to the right. So this will be a shift right by 3. But let's plug in points to make sure. So if I plug in 5, absolute value 5 minus 3 is absolute value of 2, which gives us 2. So over 5, up 2. If I input 4, 4 minus 3 is 1, which absolute value is to 1. If I do 3 minus 3, that makes 0. Ooh, 2 minus 3 gives me -1, but that absolute value is to +1. 1 minus 3, absolute value is to -2, or gives you -2, which absolute value is to +2. 0. 0 minus 3, absolute value of -3 gives us 3. Okay, and we're going to guess, say 1. -1 minus 3 makes -4, which absolute value is to 4. And okay, I think we're done now. When you plug in -2, you get 5. So you see your V graph. And if I were to sketch in that parent graph, it looks like this. And you can see that that yellow graph shifted right 3 units, gives us the graph where we plotted points. So this is a translation shifted right 3 units. Okay, great, there we go. So those are horizontal and vertical transformations. Now let's write some equations for functions where we have sort of random transformations. So if we take absolute value of x plus k, and again here you have to assume that k is positive. It's a needed assumption that I should have made. Now this will shift the graph to the left, k units. And if you do x minus k, it shifts the graph to the right, k units. All right, write an equation that describes the given translation of y equals absolute value of x. A shift left 20. So doing shifts left or right means do them inside the function. So that will be y equals absolute value of x. Now to go left, we have to do plus a constant number, so that will be x plus 20. Okay, a shift down 10. Well, in that case, we have to do something outside of the function. And in that one, it's intuitive. We just take away 10 from the absolute value. And now lastly, what if we do both, a shift down 5 and right 3? Well, let's do the right 3 first. That's going to be x minus 3 inside the function. And then down 5 will be minus 5. And going down 5 and right 3 is the same as right 3 and down 5. So down 5 over 3 is equivalent to over 3 down 5. All right, let's sketch a graph of absolute value of x minus 2, or sorry, absolute value of x plus 2 minus 5 using these transformations. So first we're going to carefully sketch the parent graph, and then using the things from examples 2 and 3, we're going to shift the graph to get the final graph. So the parent graph goes through 0, 0, 1, 1, 2, 2, 3, 3, etc. So plot some of those points. And if I give you a nice grid, I expect that you plot a function that goes through the correct points on that grid. Okay, so we're going to shift our parent function, y equals absolute value of x. First, we're going to go left 2, and then down 5. So take each point, move it left 2, down 5. I'm just going to move this vertex point. Left 1, 2, down 1, 2, 3, 4, 5. And from there, I know the slopes of the lines are positive 1. So rise 1, run 1. And negative 1, so up 1, back 1. And there is your translated function. Yay! Just for kicks, its domain is negative infinity to infinity because there is no leftmost, there is no rightmost. Its range, the lowest y value it hits is minus 5. It has no highest y value. Okay, so that's basically it for moving a graph up or down or left or right. And there are 2 more things we're going to do. We're going to talk about how to stretch the graphs and then also how to reflect the graphs over the x-axis. Okay, so here we're going to talk about stretching the graphs. So here we have 2 times absolute value of x, and we're going to see how that relates to the parent function. So if I input 3, 2 absolute value 3 will be the same thing as 2 times 3 or 6. If I input 2, 2 absolute value 2, same thing as 2 times 2, which is 4. If I input 1, 2 absolute value of 1 will be 2 times 1, or 2. For 0, 2 absolute value 0 will be 2 times 0, or 0. Negative 1 is the same as inputting positive 1, so we get 2. Negative 2 is the same as inputting positive 2, so we get 4. And negative 3 is the same as inputting positive 3, so we get 6. So over 3 up 6, over 2 up 4, over 1 up 2, 0, 0, back 1 up 2, back 2 up 4, back 3 up 6. So there's the 2 absolute value x. And just for reference, I'll sketch in the original parent graph. So that went through 0, 0 and had a slope of 1 on one side, and then a slope of negative 1 on the other side. Okay, now is this black graph taller or wider than the graph of absolute value of x? So this definitely got like skinnier or was a vertical stretch. It's definitely taller. And notice that the slopes of the 2 branches of the V are plus or minus 2. Like this slope over here is positive 2, this slope over here is negative 2. And that will always be true with absolute value functions because basically what you have are 2 lines. This number in front of it will tell you the slopes of the 2 branches, it's just that one of them is negative that number. So if multiplying by 2 makes the graph sort of taller and skinnier, multiplying by 1/2 might make it sort of like squatter and fatter. All right, here I picked some nice points to plug in so we would get whole numbers. If I input 6, half absolute value of 6 is half of 6, which is 3. Half absolute value 4, half of 4, which is 2. Half of 2, well, that's 1. Inputting 0, I just get 0. And if I input -2, it's the same as 2. Input -4, it's the same as 4. And if I input -6, it's the same as 6. So over 6 up 3, over 4 up 2, over 2 up 1, 0, 0, back 2 up 1, back 4 up 2, and then back 6 up 3. So there's 1/2 x, or 1/2 absolute value of x, sorry. And just for reference, here's the parent function. Okay, and so in that you can see that this graph that we have, 1/2 absolute value of x, that graph is definitely sort of wider than the y equals absolute value of x. And notice that the slopes of the lines are plus or minus 1/2. Okay, great. Last one. All right, so if you multiply by a positive number that's bigger than 1, the graph of that positive number times absolute value x is a vertical stretch, as in makes it taller and skinnier. And if a is in between 0 and 1, I say if a is a fraction, but you know, fractions can actually be bigger than 1, so maybe that's not the best thing to say, but some number in between 0 and 1, then this graph is a compression, meaning like a squish by a factor of a. And it should be like all the y coordinates get multiplied by a. That definitely is true. Okay, one last one. So what if we multiply by a negative number outside? Now here, just notice that that negative sign is outside of the absolute value. What this means is first you absolute value, then you make the result negative. Or you can think about this as -1 times absolute value of x. So if I put in 3, I have -1 times 3's absolute value, which is -1 times +3, which gives me -3. If I input 2, I have -1 times 2's absolute value, which is -1 times 2, or -2. If I input 1, -1 times 1's absolute value will give you -1. -1 times 0 absolute value will give you 0. Oops, whoops. -1 times -1's absolute value. Now first you absolute value this -1, which makes it +1. Then multiplying it by -1 gives you -1 again. So basically you're always going to get negative answers, except for 0. -1 times -2's absolute value gives you -2. And -1 times absolute value of -3 will give you -3. So over 3, down 3, over 2, down 2, over 1, down 1, 0, 0, back 1, down 1, back 2, down 2, back 3, down 3. So there is the V. And it's pretty obvious that this graph is obtained by taking the original parent graph and reflecting over the x-axis. Be very careful when you say flipping, because you can also flip a function over the y-axis. With these absolute values, that doesn't really make any sense because they flip onto themselves, but better to say like a reflection and then what you reflect over. All right, so last thing, write an equation for an absolute value graph that has been reflected over the x-axis, shifted left 3, and up 10. So the reflected bit means I have a negative in front of my absolute value bars. The left 3 means inside of the function, I did plus 3. And then up 10 means after that, I add 10. All right, and that's it. So go ahead and give this homework a try. No excuses. Have fun.